here in this problem, u is given as log of x cube plus y cube whole upon x square plus y square, and we have to prove that x dou u by dou x plus y dou u by dou y is equal to 1. Now to get the value of x dou u by dou x plus y dou u by dou y equal to 1, there are two methods. The one of them is we have to differentiate u partially with respect to x, so that we'll get the value of dou u by dou x. Then we'll substitute that value over here. Then we'll get the value of dou u by dou y by partial differentiating u with respect to y, and we'll substitute that value over here. And then by multiplying it with x and y respectively and adding it, we can get the value of 1. But I think that is a lengthy method. Then what is the shortcut method? So for that, if you'll observe the left hand side, then it is in the form of Euler's theorem. So by Euler's theorem, we can say that x dou u by dou x plus y dou u by dou y is equal to nu, provided the given function u is homogeneous function. So here I'll use the Euler's theorem, and for that I'll first prove that u is homogeneous function. And if u is homogeneous function, then I can apply the Euler's theorem to get the value of x dou u by dou x plus y dou u by dou y as 1. So let's start with it. So here I'll say u is equal to log of x cube plus y cube upon x square plus y square. Now to prove that u is homogeneous function, we have to put x equal to xt and y equal to yt. So here I'll say putting x equal to xt comma y equal to yt, we get, so it will become u is equal to log of x cube t cube plus y cube t cube upon x square t square plus y square t square. Now we can take t cube common from numerator and t square common from denominator, and when it will cancel with each other, we'll get t extra in the numerator. So we'll get u equal to log of t into x cube plus y cube upon x square plus y square. Now if you'll see here, then this t is remaining inside the logarithm, and hence we are not getting that original function u back. Hence here u is not homogeneous function, because for u to be homogeneous, we want this t outside the function, so that we can get that in the form t raised to n into the function. But we are not getting that form, and therefore here I'll say here u is not homogeneous function. So now since u is not homogeneous function, we cannot apply the Euler's theorem, right? But if we'll convert this u in some other form, and if we can prove that it is homogeneous, then still we can apply the Euler's theorem. So what I'll do here is I'll take this log on other side, or I'll take e as base on both sides. So by taking e as base on both sides, here it will get e raised to u, and here we'll get e raised to log of x cube plus y cube upon x square plus y square. So for this equation number 1, I'll take e as a base on both sides. So therefore we can say, but e raised to u is equal to x cube plus y cube upon x square plus y square. So log is cancelled because we have taken e as base, so that here this formula is applicable. So e raised to log of x is equal to x. So e and log gets cancelled out. So by using this formula, we got x cube plus y cube upon x square plus y square. So here if you'll observe, then I can say that e raised to u is function of u. So here I'll say this is function of u which is e raised to u, and I can say this as z also. So let's say it is z, and the value of it is x cube plus y cube upon x square plus y square. And now if I'll check for this f of u whether it is homogeneous or not, then we'll get it as homogeneous. So for that we'll put x equal to xt, y equal to yt, then we can get t cube over here, and here we'll get t square, and by cancelling t square, we can get extra t over here. So therefore here I'll say putting x equal to xt, y equal to yt in f of u, we get, so this will become, or f of u is also called as z, so this z will become, so that will become z of x comma y, and that will be x cube t cube plus y cube t cube upon x square t square plus y square t square. So from here we can take t cube common, x cube plus y cube will remain, and from here we can take t square common, x square plus y square will remain in the bracket. So therefore here we can get t by cancelling t square and t square, and in the bracket x cube plus y cube upon x square plus y square. So it means we are getting the original function z back. So I can say this is in the form t into z of x comma y. So here that function z we are getting in the form t into again the function z. So here therefore we can say z equal to f of u is homogeneous function with degree 1, because here the power of t is 1. So it is degree 1 homogeneous function, and now we can apply Euler's theorem for f of u. So therefore here I'll apply the corollary of Euler's theorem. So now I'll say therefore by corollary of Euler's theorem, now the corollary is, if z equal to f of u is a homogeneous function, then x dou u by dou x plus y dou u by dou y is equal to n f of u upon f dash of u. So therefore here we will get x dou u by dou x plus y dou u by dou y equal to, now n is nothing but degree, so here in our problem we got degree as 1. Next f of u, that is a function, and here in our problem the f of u is e raised to u. Next f dash of u is nothing but derivative of this function f of u, and the derivative of e raised to u is again e raised to u. So we can cancel this e raised to u. So therefore we will get x dou u by dou x plus y dou u by dou y equal to 1, and this is the required result. Thank you.